a production of WGBH Boston.
Tonight on Nova, superstar athletes push their bodies to the limit. Take an amazing journey inside to see what makes it all possible. Watch the body turn junk food into raw energy. Experience one climber's struggle to survive the onslaught of infection. Get up close and personal as sperm meets egg. Join us as we explore the universe within.
Funding for NOVA is provided by
Merck, dedicated to pharmaceutical research, committed to discovery, improving health, extending life. Merck.
And Lockheed, America's aerospace company, supporting math, science, and engineering education for national technology leadership. Major funding for NOVA is provided by the Corporation for Public Broadcasting and by annual financial support from viewers like you.
The human body. Driven by a great athlete's skill and dedication, the body is racing faster, jumping farther, reaching new heights all the time. But inside, a web of complex mechanical, electrical, and chemical activity is constantly underway. Countless pieces working together in nature's most fantastic machine. With a tiny fiber optic camera, an electron microscope, and cutting-edge computer graphics, techniques similar to those that first amazed the world in The Miracle of Life, NOVA now continues the journey through the incredible human machine. The trip reveals a whole universe within. Muscle and bone being built. Bursts of energy produced on a moment's notice. Invaders fought off. Precious new life created. This fantastic voyage begins with the story of a man who can fly. This man is a champion. His name is Mike Powell, and he owns the world record in the long jump. In 1991, Mike soared 29 feet 4.5 inches, nearly 10 yards, breaking a record that had stood for more than 20 years.
When I came to the stadium, I knew I was going to break the world record. I thought about it all night. I had visualized the whole jump. I had even visualized what I was going to do to the crowd after I made the jump. So I went there with the purpose.
Mike Powell is still the #1 long jumper in the world. And while he still works hard to break records, his main focus now is to stay ahead of the competition.
I used to be caught up on how far I was jumping because people would say, well, you didn't break the record. And I'm like, look, I broke the record once, and the record was broken. It took 23 years for it to happen. It's not going to happen every day. So for me now, I go for the win. When the wind is right, when the track is right, when the competition is right, when the crowd is right, when the ions in the air are right, when everything is perfect, I just try to get myself in the kind of shape where I can take advantage of the moment.
The kind of shape Mike is in combines a smoothly functioning heart to pump oxygen-rich blood around the body, large and pliant muscles to send him soaring high into the air, and beneath it all, a solid support system, the bones. To build the perfect long jumper, start with the 206 strong, light, dependable bones that form the human skeleton. Bones that are heavy enough to withstand a pounding, and light enough to get airborne for a moment or two. Simplicity and strength in an elegant design. Outside the bone is hard and solid, but inside it's porous and light. It is a design often copied by architects when strong but lightweight construction is required. The electron microscope reveals the individual bone cells connected by thin, wiry tendrils. But bones are more than support structures. Inside, they are alive, constantly building and rebuilding themselves. There are nutrient channels throughout the bone. Here is where the process of renewal takes place. Bone, when it is first built, is soft cartilage. As it thickens, it gets darker. But while new bone is being made, older bone is being destroyed. This is a bone-eating cell at work. It is estimated that the skeleton is completely rebuilt every 2 years. After age 40, the bone-eating cells begin to get the upper hand, making bones in older people more fragile. Not that Mike Powell has to worry, yet.
Now I'm 30 years old, and 30 is not old by any means, but for a long jumper, it's what they call experienced. And I use that experience. Well, everything that I do in my training, I try to make sure that is specific to what I do on the runway, and that's long jumping. All the weights that I do are very specific to running down the runway and jumping and landing. The running that I do is very specific to the kind of run that I do on the runway. With the pool, I do a lot of things in the pool concerning the long jump. I do underwater jumps, practicing my jump. I run in the pool and do drills in the pool. After the season's over, I may have 3 months off, but I'll play basketball. You know, I've been known for dunking on people and just dunking on anything. So I kind of get that residual effect year after year of training. So now my fitness level is at its highest because it's like I've been training for 10 years now.
Much of Mike's specialized training is geared toward the muscles, the moving parts that provide the body with the capacity for motion. All the muscles of Mike's leg are made up of elongated cells with energizing proteins that give them distinctive light and dark stripes. Skeletal muscle is enclosed in a membrane. At its ends, this forms the tendons, which attach muscle to bone. A cross-section reveals the individual muscle fibers inside, like strands that make up a rope. Surrounding these fibers is a network of connective tissue, nerves, and blood vessels. Closer up, we see a system of tiny vessels that store calcium ions needed to trigger muscle movement. In the fiber are the muscle proteins, actin and myosin. Shown as pink and white rods on the screen, these two proteins tug and pull each other. When repeated across the millions of cells that make up a muscle, this microscopic action gets the body moving.
As an athlete, you have to know your body so well. My body now is at such a finely tuned level that I have to be careful with everything that I do. I can't run out and just go play basketball or go jump over a car like I used to because any little thing can throw it off. But this love is to be very precise about what you do. Like for myself, I know when my heart's not beating right. I can tell when my heart's beating too fast. I don't have to try it. I don't have to test it.
A double action pump of ingenious design, the heart is the engine that drives the human machine. The heart and its network of blood vessels keep every part of the body supplied with a steady stream of life-sustaining oxygen. The oxygen enters the bloodstream through the lungs on either side of the chest. The heart takes in this oxygen-rich blood through the left atrium, the top left chamber. It flows down to the lower chamber, the left ventricle, and the ventricle pumps the blood up and out to the body. Emptied of oxygen, the blood returns to the heart through the right atrium, passing into the right ventricle, which pumps the blood back to the lungs. These tendons on the heart's inner walls are attached to muscles that contract to regulate the amount of blood flowing through the heart. Valves open and close. Blood enters and exits, creating a familiar rhythm. But what keeps the heart on the beat? Even when taken out of the body, an isolated piece of heart muscle will pump without any signals from the brain or the nervous system. Here's another. And another. But how can all these muscle cells, each capable of independent action, work together in the heart in perfect synchrony? The secret lies with the heart's spark plug, the sinoatrial node. Called the SA node, it is located at the top of the heart. Its signal is picked up by the AV node near the ventricles. Left to their own devices, the muscles of the heart would only beat about 40 times a minute. But the SA and AV nodes send out electrical impulses that synchronize the beating and boost the heart up to a more normal speed. About 70 beats per minute, 24 hours a day, 365 days a year. Here, we see the entrance to the coronary artery, where blood enters to fuel the heart muscle itself. Fully 10% of all oxygen taken in is used to keep the heart pumping. Any muscle can cramp if its oxygen supply is cut off. For the heart, a cramp means a heart attack, the devastating result of a blocked coronary artery. This is the top of the heart looking down through the aortic valve. Here is the entrance ramp for the blood's main highway. Oxygen-rich blood is launched up and through the aortic arch, setting out for every distant destination in the universe within. The first set of exits off the highway lead north. The opening on the right leads to the arms, while the two openings on the left will carry 15% of the body's blood supply to the brain. Passing this interchange, the road turns south. The two lights at the end of the tunnel lead toward the legs. The side roads above and below supply the abdomen. Blood that makes it all the way to the end of the road, the feet, branches into countless tiny vessels, the body's best attempt at keeping the toes warm on a cold winter's night. The hands, too, are shot through with tiny blood vessels. The fingertips are particularly well provided for. The electron microscope reveals another intricate net of blood vessels, this one supplying the tiny cochlea of the inner ear. Though only the size of a pea, this sound-sensitive organ is one of our most important links to the outside world.
What attracted me, for me, I look at myself as like almost like an entertainer. So when I'm out there, I feel like I'm entertaining the crowd. So as opposed to trying to block things out, I'm trying to encompass everything and bring everything in. Like, okay, everybody watch this over here. Watch what I'm about to do.
Representing the USA, a two-time world champion in the long jump. Ladies and gentlemen, this is world record holder Mike Powell.
Mike's machine is tuned and ready to follow the orders sent out by the brain.
I think about trying to jump out of the pit, and after I get that emotional charge of how far I want to jump, I then just go through my technique. I have different phases, and I go through my walking phase and my drive phase and my sprint phase and my takeoff phase, and then my jumping, and I visualize the whole jump in my head, and then I land, and then I hear the crowd, and then I go do it.
Mike decides to move. His brain sends a signal to the nervous system, setting into motion an amazing series of events. Here, a muscle cell appears as the dark streak running down the left side of the screen. The thin hair-like structure to the right is a nerve. It reaches out to make contact with the muscle. In this electron microscope view, the nerve cell has been dyed yellow. The nerve is the brain's communication link to the muscles. The more points of contact between a nerve and a muscle, the more efficient the communication. When Mike decides it's time to go, his brain alerts the appropriate nerves. The nerve stimulus arrives at the muscle in the form of an electrical charge, passed along through a chain of chemical interactions. The problem is to transform this electrochemical impulse into physical movement. It's a trick the body is constantly performing. In less than 1,000th of a second, the nerve impulse spreads across the surface of the muscle fiber and dives down into its interior. There it releases stored calcium ions. These calcium ions instantly alter the chemical environment of the muscle. Just as lightning sends an electrical charge through the air, the calcium sets off a chain reaction, sparking the proteins actin and myosin to create movement in the muscle.
And now for his last jump, Mike Powell.
Jumping with a sore hamstring, Mike is not likely to break his record in this track meet. Going into the final jump, he's in 4th place. But even with his body in less than peak condition, a champion has his pride.
I love competition, and I love to win, and that's a lot of motivation. And I have a good time at whatever I do. So I have fun when I train, have fun when I compete, and I have even more fun when I win.
The jump is over in the blink of an eye, but a look in slow motion reveals the champion at work. Muscles, bones, heart, and mind working together to produce an explosion of power and grace. The human machine striving to perform at its peak.
Mike Powell, winner of the long jump, 26 3¾ on his last attempt.
Well, my jump was ugly, and I won, but I still love Nova. Peace out.
Speed skating, The power, the grace, the controlled 30-mile-an-hour sprints around the track are the result of an unending series of demanding workouts. Here in Milwaukee, the United States speed skating team is preparing for another grueling season of competition. For five-time Olympic gold medalist Bonnie Blair, it will be the last.
I'm definitely looking forward to the World Championships here in Milwaukee, you know, kind of my own home turf. Also, I feel that being able to kind of finish up at home is going to be a nice feeling. My whole family's going to be here, friends. I don't know how many they're expecting this time, so I'm definitely looking forward to it.
Team training involves weightlifting. Torturous set of isolation exercises called plyometrics. And every other day, they spend the afternoon running up hills. All this activity takes a lot of energy. And at 5'4" and 130 pounds, Bonnie is hardly superhuman. So what's the secret of all that record-setting speed? Is she on a special diet? Space-age formula of vitamins and proteins?
One thing that people have kind of always teased me about is usually day competitions, I always have a peanut butter and jelly sandwich. And, you know, that's just been something that's worked well for me. I enjoy that. That's probably one of my favorite lunch foods anyway. So, you know, when you are at a competition, sure, you're going to have some nerves. And so you have to find something that's going to sit well with you in your stomach. And that's important. And to me, a peanut butter and jelly sandwich is what works best.
For a jolt of energy, there's nothing quite like the sugar and carbohydrates in Bonnie's snack. They're very close in structure to the fuel the body uses, glucose. But a quick fix will only last about 20 minutes. To make it through her day, Bonnie needs a huge amount of energy, stockpiled for use a little at a time. The way the human body manages this is to convert everything we eat into a few basic components: instant and storable energy, vitamins, nutrients, and waste. In a process never to be discussed at the dinner table, here's what happens after we chow down. The first stage of digestion is simple. Moistened by the saliva of the mouth, muscle contractions move the food down the gullet toward the stomach. Here, whatever we've taken in will be turned into something more manageable. Although it doesn't look it, the stomach is a muscle, a smooth muscle. It flexes over and over again, slowly squeezing whatever we've eaten into pulp. Depending on the food, this process can take up to several hours. While enzymes help break the food apart, industrial-strength acid surges in from 1,000 tiny jet streams along the stomach wall. A closer look reveals the microscopic glands that manufacture more than 3 quarts of gastric juice a day. It's a powerful brew, mostly made up of hydrochloric acid, a substance that can turn metal to mush. What keeps the gastric juice from eating the stomach itself? The answer lies in the shiny reflections on the surface. They are part of the mucous membrane, the thin protective layer that not even hydrochloric acid can penetrate. Salt, alcohol, and certain other foods can, and too much of any of them may result in an ulcer. The burn marks on this stomach wall show what the acid can do if the protection of the mucus is stripped away. While stomach ulcers have most often been blamed on diet and stress, recent studies indicate certain bacteria can also be the culprits. A healthy stomach can break down just about anything we serve it up.
I'm actually lucky that I'm not too regimented. I'm not too picky about what I eat. Being an athlete, you do try to get a lot of carbohydrates in, so, you know, some pastas, but I also grew up being younger, meat and potatoes type person, so, you know, I like my meat and potatoes. I'm not a real big vegetable eater, but I do have something green every day, and, you know, whether I chase that with milk or whether it's a salad, which I enjoy, then that's okay, but sometimes I have to chase those vegetables with milk. I like to snack on chips and probably like candy bars like Snickers or something like that, ice cream. I love chocolate chip cookies. Of course, actually I probably like the dough better than the actual cookies, but those are my favorites. Might not sound all that healthy, but then maybe I come back with yogurt and that's better.
If you think Bonnie's diet sounds good, be prepared to train as hard as she does to burn it all off. Thoroughly massaged, the sandwich is passed down the disassembly line to the duodenum, the top of the small intestine. Here, it gets a rinse as intestinal juice, pancreatic juice, and the bile are all added. The dirty-looking bile is really a cleanser, manufactured by the liver and shot in from the gallbladder. It breaks large globules of fat into fine digestible droplets and helps pancreatic juices neutralize acids from the stomach. The gallbladder concentrates and stores the bile until it is needed. If the concentration gets too great and is made up of too much cholesterol, gallstones can result. These are gallstones, old bits of cholesterol, bile salts, and pigments that rolled around together until they collected into little balls. They're not a real problem until they get stuck in the bile duct. Then, until they pass, they become the source of excruciating pain, and usually a resolution to eat less fat. By the time our meal reaches the small intestine, it has been turned to soup. From here, useful nutrients will be taken up by the body, while muscle contractions draw the fiber, other undigested substances, and water into the large intestine. The journey through the large intestine can take up to 12 hours. Needed fluids and water are removed, along with most of the bile that was added. The bile that remains accounts for the brown color of human waste. These are bacteria feasting on our food remains. These helpful microbes produce vitamins and consume leftover nutrients and oxygen, causing intestinal gas in the process. Under regular conditions, 25% of human waste is made up of these friendly bacteria. The process of the body taking what it needs from the food we eat is called absorption. This takes place here, back in the small intestine, where the body soaks up the good stuff for distribution. But bacteria are also present in the small intestine. How does the body absorb nutrients while screening out the bacteria that could be dangerous in other parts of the body? These tiny finger-like projections that line the small intestine walls are called villi. Like a super absorbent rag mop with filter attached, the villi are able to soak up the nutrients and leave the bacteria behind. Here's how it works. On the top, each villus finger are 6-sided cells, 1/10,000th of a millimeter across. The bacteria are too big to fit between these tightly knit fibers, but glucose and other nutrients easily slip through. Here at the cell's surface, tiny greenish fat globules float right in. Enzymes, here looking like red jelly beans, turn complex sugars into simple sugars that can be pulled into the cell through openings in the cell membrane, seen here as cups on the cell surface. Now it's on to the bloodstream. Some of the sugar goes directly to the muscles, but that can only power us for brief spurts. The rest needs to be stored for when we need it. Bonnie's snack is now being put to use. Her sandwich, the yogurt, and a few crispy tortilla chips have been broken down. The high-octane fuel pulled from them, glucose, powers her every stride. But it takes more than raw fuel to make a champion.
I've been real lucky to be able to work with the men on our team, and they've been very helpful to be, in a sense, bring me to speeds that I would never be able to go on my own. Being able to skate behind them, skate in their draft, has been a very big plus for me. You know, I'm lucky that my boyfriend's in the sport, and I can be his shadow. Even sometimes he likes to be my shadow. It's been said I've been one of the better technical skaters in the sport, so a lot of times then he likes to skate behind me just for the technical aspects, where I like to skate behind him for more of the speed aspects of the sport. So it's kind of nice to be able to have your best friend there with you all the time, going through all the workouts day in and day out, be there to supporting you, help you when things are going wrong, and pat you on your back when things are going right.
Perfect.
I'm just not strong enough.
Back inside the body, this is the liver, the largest single organ we have, the regulator of our energy needs. This is where proteins, fats, and carbohydrates not put to immediate use are sent. Centrally located above the intestines and below the diaphragm, the liver is a multifunction workhorse. It's a storage battery, recycling center, health club, and detox unit all rolled into one. The liver is made up of a forest of blood vessels that connect millions of tiny working units. These working units preserve the body's delicate chemical balance, making the liver one of the most complex and well-run factories on Earth. The moment the digested sugars from Bonnie's sandwich enter the liver, they are met by teams of enzymes, here imagined with mechanical arms. The enzymes grab onto the glucose molecules and assemble them in a chain called glycogen. These chains, connected together, form balls of glycogen, the body's pep pills. They're stored in the liver and throughout the muscles. Between meals, the liver converts the glycogen back to glucose and releases it into the bloodstream to supply the body's energy needs. The steady flow of glucose is essential, not only for champion athletes, but for all of us. The brain, for example, runs entirely on glucose. Too much or too little can have effects ranging from minor disorientation to coma or even death. The liver is also able to manufacture many different proteins. These boost muscle and bone growth and give blood the ability to clot. The liver's protein factories, here lit up like spaceships, are called ribosomes. The snake-like ribbons flowing toward them are messenger RNA molecules, each one carrying the blueprint for the assembly of a single protein. In a fantastic display of assembly line engineering, building blocks called amino acids are hooked together in a precise order to form long protein chains. Inside the ribosome, the protein chains are further processed into a stable form that will allow them to perform their assigned tasks in the body. A million proteins are produced every minute. With the new protein complete, it's time for the rollout, out of the liver and into the bloodstream for distribution. For the blood, the liver serves as both health club and detox unit. It constantly checks for levels of cholesterol and poisons of many types. If there is too much cholesterol in the blood, the liver removes the excess, recycling some of it into bile. The bile and some leftover cholesterol are then shipped to the gallbladder. And here's the detox unit. These beautiful crystals are benzopyrene. They're found in cigarette smoke and car exhaust. Getting a good look at a poison like this, the liver sets up a machine shop, engineering an enzyme to clean up the toxic spill. It can do this for many dangerous substances, up to a point.
You know, sometimes I can have like one beer and it's weird. I don't know whether it's just being an athlete or what. It feels like it goes right into my legs and my legs feel funny from that. You know, so that's sometimes where, you know, that's something you almost try to tend to stay away from a little bit, especially during especially during a heavy competition season.
Under normal conditions, the body can process a small amount of alcohol with no problem. The trouble starts when things are taken to excess. A few drinks and an empty stomach can have an immediate negative effect. The alcohol gets past the mucous membrane and kills some cells in the underlying blood vessels, causing bleeding to occur. Aspirin and excessive amounts of salt can do the same thing. Seen under the electron microscope, the damage to the stomach wall appears devastating. But the body has an answer for these everyday assaults. The undamaged cells surrounding the injury rally to the cause, stretching out their tendrils until they reach one another, making a healthy net over the damaged area. This quick repair process takes about 30 minutes to complete, if it's not needed too often. In the liver, these lobes are in more serious trouble. Weakened by virus or parasites or the long-term effects of alcohol, they are unable to process all the food that is entered. Instead, the food turns to fat, here tinted blue. The fat fills the liver lobe until the cells burst. The dead lobe is replaced by simple connective tissue, and some of the liver's working capacity is lost. The surviving liver cells must do even more. If they too are overstressed, more cells will die. Cirrhosis sets in. Unchecked, the connective tissue will be all that is left. When too much of the liver goes, we go with it, because there's nothing in the body and nothing we can build to replace it. These Japanese engineers tried to design a chemical plant that would work like the liver, but as they discovered, the chemical engineering carried out in the liver is more advanced than anything modern technology can offer. An enormous factory would be needed just for the energy distribution system, and handling the toxins was just overwhelming. The healthy liver takes care of us day in and day out. And like the champion athlete who makes everything look easy, its astounding abilities are sometimes overlooked.
I never got involved in the sport of speed skating, you know, to be able to make money out of it. I knew that that was going to be very slim, few and far between. I got into the sport of speed skating because I love what I'm doing. I love that crack of the gun, the thrill of competition. I look forward to it. I'm never scared of it. But now I'm getting to the point where I want to kind of go on and do other things in my life, and I'm looking forward to that as well.
Ready?
Ready.
1 minute. And begin.
Karen Hatchett Pavlin is in training. Once one of America's elite track and field athletes, Karen is now preparing for the biggest event of her life, the birth of her first child. Although there's no medical evidence that being in shape leads to a smooth delivery, Karen is convinced she has a big advantage going in.
Try and visualize it.
Being in good condition means being in tune with your body and being able to listen to and respond to whatever your body's telling you. Being in good shape really, really has given me that kind of advantage, hopefully. We'll see.
Okay, concentrate, focus back in.
For husband and coach Rob Pavlin, training for this event is very different from when he coached Karen at the track.
And I was really able to detach myself from her at that moment, that she was just somebody who was running that needed encouragement and sometimes needed to be encouraged softly and sometimes needed somebody to tell it just to go run and stop complaining and just get it done and so we can get out of here. But now it's like, you know, when she says to me, look, I'm really tired, can we, you know, I just melt. I mean, because now it's our experience instead of just her experience, and that's a big change.
It's a connection.
Good. Oh, God, feel that. You feel an arm there or something.
As Karen and Rob prepare for the big event, their baby is nearing the completion of a process that began 9 months ago
Hi, Zuri.
with a single cell.
Okay, come on, let's go back.
A woman is born with all the egg cells that she will ever have. There are about 1 million of these primitive cells called oocytes. By puberty, this amount is reduced to 400,000. Over the course of the fertile years, only 400 eggs will grow to maturity. 400 chances to make a baby. Here, with the addition of a ring of supportive nurse cells, an oocyte has developed into a follicle. Several follicles are created each month, but only one continues to develop into a mature egg. Every oocyte and every sperm carries the unique combination of genes that make up our inherited characteristics. Here, the egg is collecting all of its genes in a little sac. The sac is then broken down and dissolved. The gene pool divides in half, and one part is pushed out of the egg. Out of 46 chromosomes, 23 are left, the mother's share of a child's biological inheritance. The eggs are held in the woman's ovaries, the almond-shaped organs connected to the uterus by the fallopian tubes, or oviducts. The man's reproductive cells are found inside the 300 feet of coiled passageways within the testicles. At birth, they are immature, lacking tails. Beginning at puberty, the sperm mature at a rate as high as 1,000 a second. The dark blue rods are the 46 chromosomes, the man's genetic identity. But as this primitive sperm divides, 2 cells are created, each carrying just 23 chromosomes. The sperm now grow tails to help navigate the long trip to the egg. When the 23 chromosomes contained in any one of these sperm combine with the 23 chromosomes of a mature egg, the result will be a new combination of 46, the blueprint for a completely new human being. In the ovary, the monthly process of ovulation is about to begin. First, a single follicle expands like a bubble on the surface of the ovary. The bubble ruptures, and the egg's nurse cells are propelled out, seeming to lay out a protective carpet for the egg. These are the first pictures of ovulation ever photographed. The egg is gently caught by the frilled edges of the fallopian tube and led into the narrow channel leading to the uterus. At first, tiny muscle contractions in the fallopian tube push the egg along its way. But then the cilia take over, millions of microscopically fine hairs that slowly sweep the egg along, So slowly, in fact, that it takes 4 days for the egg to reach the uterus, longer than it can survive on its own. If a baby's to be made, the sperm will have to join the egg here in the fallopian tube during the brief period when fertilization is possible. The sperm arrive on the scene during sexual intercourse at the moment of ejaculation. At male orgasm, typically several 100 million sperm are ejaculated into the woman's vagina. They have a common goal: get to the egg and fertilize it. Only one, if any, will succeed. Millions of sperm die at the first pass, destroyed by the vagina's protective acidic environment. The survivors continue up to the cervix, the entry gate to the uterus and egg beyond. If a woman is not ovulating, the secretion barrier of the cervix spells doom for the sperm. There is zero chance of getting past it. Folds in the mucous membrane trap the sperm, and they struggle to escape for up to 3 days before they die. But during the few days of ovulation each month, with the mature egg waiting, the impenetrable gate of the cervix opens, ever so slightly. Sperm are still trapped by the thousands, but a few find the microscopic channels created in the secretion barrier by the release of estrogen. The surviving sperm are halfway home. They push on through the uterus up to the entrance to the fallopian tube. Of the 300 million that began, perhaps a few thousand remain. Now, within striking distance of their target, they prepare to do what they've come for: fertilize the egg. Just past the fallopian tube entrance, the surviving sperm suddenly stop and rub themselves against the cilia. It is possible that this is the moment when a covering of protein molecules on the sperm surface are stripped off. With the covering removed, the sperm, for the first time, are ready to deliver their chromosomes, fertilizing the egg. So close and yet so far. Of the thousands that make it as far as the fallopian tube, only a few hundred reach the egg. When they get there, they encounter the final and most imposing barrier of all, the egg's protective shell. On the cellular level, this dense cement-like ring is the equivalent of a castle wall 30 feet thick. Special measures are called for. Arriving at the egg, enzymes carried in the sperm's body rush to the surface and form a chemical battering ram. The chromosomes remain in the sperm head, but the tail, powered by energy capsules called mitochondria, changes its motion from regular waves of movement to quick, strong, whip-like lurches. An amazing effort, but without the cooperation of the egg, it probably wouldn't be enough. The support cells that now make up the wall of the egg are changing shape, weakening the wall just enough to draw the sperm in. The sperm keep trying, the explosive energy of their tails driving them along. Most of the remaining sperm die in this last attempt to penetrate the egg. Finally, success. A single sperm has broken through. Instantly, a burst of electrical activity changes the surface of the egg, making it totally impenetrable. 300 million sperm set out. One made it to the finish line. The sperm continues to move for a short time while inside the egg, and then its tail drops off. The sperm's head slowly starts to swell until it is 200 times its original size, preparing to combine its genes with those of the egg. The two large, round structures hold the ingredients for a new human being. Half the genes from the woman, half from the man. Now, the moment of fertilization. The two pools of genes appear here as the two interlocking circles. they fuse with immense power. United, they dissolve into the egg, and the blueprint for a new individual is set. A combination of inherited characteristics unique in all the world has been created. Almost immediately, the egg divides itself into two identical cells. These daughter cells are the first of the billions to come that will culminate in the birth of a single new human being, or maybe more. Mother-to-be Karen Hatchett Pavlin is an identical twin. Like Karen, her sister Kim was also once a track star. Today, Kim is an investment banker, and Karen is an account executive for Xerox. Like many twins, Karen and Kim are close. Sometimes they believe they can even sense what the other is experiencing.
It just had a very, very strange feeling when she called. And I remember Rob was away, and I just knew she was pregnant. I just knew it was it. And it just convinced me just to go ahead and take the test and find out. And she was right. We were really excited. Yeah.
So you knew before Rob knew?
He's not supposed to know that. Being twins, we always wondered if Kim was having this baby with my husband, if the baby would look a lot alike, or if they would look like twins, or obviously they would look like brother and sister, because we're genetically the same. So it's an interesting thing. It's an interesting experiment for maybe not us, but somebody to do.
Much of who we are as people is determined by our genes. Eye color, hair color, looks, even some personality traits. And all of this is set in the first moments of pregnancy, when maternal and paternal genes fuse together. In the first few days of pregnancy, the egg cells continue to divide as they slowly float down the fallopian tube toward the uterus. Sometimes, about once every 300 pregnancies, this group of identical cells may divide in half. Identical twins like Karen and Kim are the result. Fraternal twins develop when two eggs escape the ovary and are fertilized by separate sperm. By day 4, the egg finally reaches the uterus. Now a startling change takes place. The cells begin to differ from one another. Within the egg, a dark-colored blastocyst develops. This ball of cells is preparing to leave the egg behind and move on to the next stage of development. In this process, never before seen on film, the blastocyst shakes the egg like a baby chick about to hatch. After a moment, it succeeds in freeing itself. Once the healthy blastocyst has separated from the egg wall, it floats freely in the uterus. Close up, the blastocyst shows its makeup. The light round cells on the lower right will become the placenta. The dark mass on the upper left, the embryo, which will grow in 9 months into a new baby. Day 5, and the blastocyst finds its way to the uterine wall. Its sticky surface helps it adhere, and the blastocyst implants itself. Sometimes the process doesn't work just right, and the body is quick to respond. Here, 3 round chromosome sacs lie inside a fertilized egg. This occurs rarely, when 2 separate sperm have both managed entry to the egg. Because of the extra half set of chromosomes, this egg could never develop into a normal human being. The body recognizes the problem, and the egg is rejected. These early miscarriages often occur so quickly and automatically that the woman hardly has a chance to register that she has been pregnant at all. Day 21, 3 weeks after fertilization. Clear as glass, the developing heart begins to beat. Blood cells appear, running backwards and forwards in newly constructed blood vessels, their thin walls providing the developing tissues with oxygen. At 4 weeks, the heart beats on, ever stronger. The beginnings of a head and face have appeared. This is the start of an eye. The liver takes shape to the left of the heart, the spinal column below. The embryo of almost any animal that has a backbone, from a fish to a tiger to a human being, looks just like this at this early stage of development. But now, in the human embryo, millions of years of evolution are compressed into a few short months. 4 weeks. The embryo is 4 millimeters long. The arms appear as narrow protrusions. This part will grow into a hand. 5 weeks. Primitive fingers have become apparent. The frog-like webbing between the fingers gradually recedes. Week 16. Hands and face are clearly recognizable. The fetus floats in the uterus, surrounded by a protective fluid sac. This flexible coil is the umbilical cord. The umbilical cord belongs to the fetus, but it is connected to the placenta, the vital link between fetus and mother. The placenta, firmly rooted to the uterine wall, is made up of an astonishing network of blood vessels. From the early stages of pregnancy, everything the fetus needs to survive and grow passes from the mother to the fetus through the placenta. In this animated view, the mother's blood, carrying nourishment for the fetus, passes through tiny holes into the placenta's many chambers. What look like trees inside so many boxes are really the branched endings of the fetus's umbilical cord, the villi. The mother's blood must stay separate from the fetus. So how is the fetus nourished? A closer look reveals the secret. The surface of the villi is made of a selectively permeable membrane, a strainer. It allows nutrients from the mother in, but keeps her blood out. The nutrients seep through the membrane into the fetus's blood supply. This system protects the fetus from some harmful substances, but cannot keep alcohol, certain drugs, and some viruses from passing through. This view shows what the process looks like inside the body. Mother's blood shooting into the exchange chamber and bathing the villi, dangling down on either side of the screen. This animation shows the mother's antibodies surging along with the blood into the exchange chamber. For 9 months, the fetus is protected and nourished in this way. And it grows, readying itself for a new life in the world outside the mother. This is an ultrasound picture of the heartbeat just before birth. Now, 18 hours into labor, the baby's condition is carefully monitored, and Karen's endurance is put to the test.
Contraction begins.
Right, here it comes. Deep breath. Breathe it out. Good. Another one. Speaking. One more, come on. Stay with it. Good job. Another one. Stay with it. Say one more, son.
Funding for NOVA is provided by Lockheed, America's aerospace company, supporting math, science, and engineering education for national technology leadership.
And by Merck, dedicated to pharmaceutical research, committed to discovery, improving health, extending life. Merck.
Major funding for NOVA is provided by the Corporation for Public Broadcasting and by annual financial support from viewers like you.
This is PBS.